Welcome all. The MFPH Next Generation Seminar Series is a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillant intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Feeds Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, the Seneca, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques et des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Mr. Avinaba Mistry from the University of New Brunswick. Notre invité aujourd'hui sera Monsieur Avinaba Mistry de l'Université de New Brunswick. His talk will be on dynamic contagion spread modeling over emergent spatio-temporal contact networks. La présentation portera sur la modélisation dynamique de la propagation d'une contagion sur des réseaux de contact spatio-temporels émergents. Thank you very much for being here. And the floor is yours, and you can start sharing your screen and talk. Thank you very much.
Thank you for the introduction. Hi, I'm Avinaba Mistry, and today's talk is fortunately just going to be in English. I'm not so well versed in French, so thanks for showing up, and definitely thanks for the opportunity to speak here. If at any point you feel the audio or the video is not working, please give a shout out. And without taking more time, I'm going to share my screen. Here we go. I hope my screen is visible. And as the name suggests, it's dynamic contagion spread modeling over emergent spatio-temporal contact networks. I'm part of a research group primarily consisting of UNB students, Bilal, Gaia, Jared, Robert. We are supervised by Dr. Sarah and Dr. Ray, and partnered by Dane Shepherd from the Black Arcs. And this work has been supported by MITAX, the Atlantic Association for Research in Mathematical Sciences, obviously the Black Arcs, and produced by UNB. This talk is roughly divided in 4 parts. We'll introduce the problem, we'll jump a bit, we'll talk about the framework, and then talk about the background, what led us there. Then we go in detail in parts of the framework and how does that work, and we'll conclude with future work. The motivation for this research project was to facilitate a fine-grained contagion intervention strategy and planning for public health policymakers. And here we see a subset of intervention measures that's taken directly from the website of Government of New Brunswick. This was during the time of October, September 2020, where we have intervention measures in the forms of household bubbles, masking, businesses, and types of businesses, and levels of it. It gets increasingly tough to model all this in, say, ODE or stochastic ODE, even with heterogeneous mixing in places, and figuring out the right parameters to match. One way we would see we might be able to keep that inherent heterogeneity alive is via a contact network. So again, this was the overarching goal, that we'll have to figure out a way to capture the heterogeneity of the geography, the population. so that we can account for individual level human mobility, and also the rapidly changing contagion intervention measures and the existence of multiple strains and intervention measures, including pharmaceutical and non-pharmaceutical ones, where masking affects the disease dynamics, and so does having a vaccine. So before going to the background, overall idea was to have different parts of the framework come together in the simulation, where the disease model can be made separate from the non-pharmaceutical intervention, which just takes in a contact network, which may or may not be produced from real-world data or from a synthetic data. So the way we went forward was one of the most heterogeneous modeling framework would be to model the movement as well as the disease dynamics as agents, because this helps us ask questions like what happens if we have uh, this proportions of infectious population in a particular space going about their day. This also helps us ask questions like what if we introduce masking on a specific venue or for a specific age group? What does that happen? And as an example, this has been utilized in modeling these kind of problem statements where we introduce a change in the system and observe the individuals, and introduce changes in individuals and observe the system. But these are also terribly computation hungry. So, but what we can take away from it is we can take the mobility part of it and generate a contact network from it, which still preserves a little bit of the heterogeneity without having to resort to a full homogeneous mixing assumption in traditional ODA-based models. And this is where our partner organization, Cityscape, uh, uh, the software from the Black Arts comes into picture. So on the bottom left, we see human mobility simulation of, of a small area. And on the right, we see how that is made. So the map layer is powered by OpenStreetMaps, from which we get the road networks, the building types, and land usage types. The population layer is synthesized based on census data available, um, um, from which we generate individual level population, which follows the the same aggregated census parameters that we have. The Tasha layer is the one uh, uh, that models the daily movement of these people based on their age, occupation status, and so on. On top of which, we can build obviously the health layer that we are going to talk about in this talk. And beyond that, we have the visualizations of various scenarios. The TASHA, or the Toronto Area Scheduling Model for Household Agents, is a microsimulation model based on surveys and has been validated for the Greater Toronto Area. It takes in origin destinations surveys and puts a cost matrix for the amount of time it takes for a person to reach from point A to point B. You um, so these and the resource sharing happens at a household level. For example, a car, where the non-negotiable trips are for regular work or school. Uh, the choice of the individual agents are usually for their leisure and shopping activities. But from this, the output that we get is something like this. that we have a, a gap chart uh, with number of agents simulated, and we get on for a particular day the time they have spent in a particular location. And given this individual level time spent, we can come back to it and figure out uh, possible contact events between two agents. Now, I'm guessing most of you are familiar with the SIR model and corresponding steady state equation. Uh, the biggest trouble, even if we manage to capture the dynamic of a disease through this kind of modeling, is how do we go about um, uh, recommending public health on reducing the beta parameter. Um, to bridge that gap, we will be looking at individual level disease transmission uh, as a way out. And one of the earliest researchers that did this was a citizen experiment, citizen science experiment. It was a small town in UK called Haslemere, and as part of a BBC documentary, 469 participants were logged of their location data for 3 days, and pairwise distances were calculated, and a social contact was defined as any event that had two of the moving objects as people within the radius of 4 meters, which finally built the social network. This is why the social network is emergent and both captures the spatial and the temporal dynamics. This research was utilized by one of the earliest um, uh, COVID papers that showed utilizing a real world network model um, and capturing the network dynamics and running uh, a disease transmission simulation with and without intervention measures reflects huge uh, possibility of life being saved. So, armed with this knowledge, uh, we went forward and figured out okay, so we have a way to introduce masking or household bubbles as uh, to be incorporated in the network-based disease modeling. So we took a look at how do we incorporate testing, because the tests that we have are of different true positive and false positive rates, and uh, part of the challenge for public health is of a logistic one on resource planning and sharing and coming up with strategies. Um, and since none of the real world tests are perfect, we figured out a way from the literature to take this into account. So, so, and since these are individual level models, we figured out how to incorporate contact tracing, vaccination, and other NPIs. The way we did that is instead of looking at the stock and flow diagram of a disease model as individuals belong, a number of individuals in a particular compartment, we are treating a disease model like a state machine, or for or just as a directed graph. And from a computational standpoint, we can encode this directed graph as a transition matrix, which just which makes our computation load much faster, and increasing the number of compartments or complexity in the underlying disease model just increases the possible, I mean, the corresponding transition matrix. Um, Moving on, where any non-infection transition is just like a Markov chain, we look at row-wise. So an infectious person may move to removed state. Um, and we just have to look up all the all the entries on that row and calculate the probability without having to worry about how their transition history. Um, Now, coming back to the Gantt chart view that we saw as an output from our partner organization's uh, software, what we have is a bunch of agents and their occupancy of the location per given time. So, which is just a mapping, and at the end of the day, a contact event is for two agents uh, is just for x and y, and a given time index is the time t if we are aggregating all the contact events between those two agents, or or a sequence of t's if we are considering the location of the agents for that contact as well. So we see over here agent 1 and 2 were at location 2 for this amount of time, and agent 4 and 1 for the overlap was around this orange, and we have agent n and agent 2 over here, and so on and so forth. And now, instead of looking at the list and the overlaps of contact events, if we look at this as a network, we we have the contact network, and we can encode that in a n cross n matrix, and there we have it. Um, Here, the overlaps uh, are encoded with colors to designate locations, and the width is encoding the time. Um, Now, for the infection probability function for each of these events, at at the simplest possible condition is just a function of the contact time t between, say, a person who is infectious and person who is susceptible. But of course, we can, once we uh, select such a function that serves our needs, here we are using the tan-h function because it asymptotically reaches 1, and it serves the purpose of a ramp-up time and monotonically increasing function as well. We can augment this with a base infection chance for different strains, and we can scale the relative infectivity of a particular viral strain and also incorporate the vaccine efficacy of the number of doses of the susceptible person as such. Now, for vaccination, the state machine of an individual may just be replicated because based on the observational data that we have, it changes the chances of infection, and it also changes the amount of days a person may stay infected or infectious. So again, for a much larger or more complex model, we can apply the same idea. To account for diagnostic testing, uh, we all we have to do is define um, new transitions. For example, the solid arrows are disease status-based transitions, and the dashed arrows are are as a result of testing. In this particular example, imagine there is only voluntary testing by the unconfirmed infectious population. We may assign a probability for a given individual at any given day. If they are unconfirmed and infectious, they might request a test and they might stay isolated till they receive a result. Depending upon the efficacy of the test, they might receive a positive result and they can stay isolated and do not participate in further uh, um, uh, spreading the infection. But they might as well get a negative result and stay part of the participating population and spread the infection. Now, when we introduce contact tracing, however, um, each for the base SIR model, it the model augments as such. If um, depending upon the contacts traced for the isolated positive population, we might test an individual who is susceptible or in the removed state, and again because of public health uh, ins- uh, instructions or mandates, they might have an isolation period where even if they are identified falsely positive, they will not participate in the simulation. And ha- but this is how even complex submodels of contact tracing may be introduced with this framework. Now, this is again just another model with a little more complexity where we try and have compartments that we can observe. For example, say we have compartments for hospitalization and hospitalization with ICU, and we have recovered and death states for individuals as well. Um, so this is for a single strain uh, and uh, and a zero vaccination, but as we have seen before, augmenting the infection uh, probability function and replicating these models and providing transitions for vaccination rates, we can increasingly capture more and more complex behavior with respect to the observable data. So after doing all that, we have to simulate. And the simplified simulation loop is as written as such. We figure out if for people, uh, we have a vaccination step, we have a voluntary test request step, and we have a result generation step, which might feed into the contact tracing step. Uh, um, and up till this point, we are figuring out what happened yesterday to figure out for who are the individuals who will be participating in propagating the infection the next day. That's the propagation step. The evolution step is just the non-infection transitions, which occurs independently of each other as part of Markov chain, not completely a chain. So this with this kind of framework, when we implemented this in R, where we put the full framework and with Julia simulation loops, these are number of seconds it's taking for us to simulate 210 days simulation, which each time step of 1 day for a population size of around 4,600 of a small town in Campbellton with four initial number of individuals and just a single viral strain. Um, so we're moving on to a few of the results. So this is how we visualize results. So imagine a single scenario, and here we have the total active cases that we are observing. Um, the very light clouds of lines are individual single runs, and but it's useful to visualize the risk of the infection as the median of running median or day-wise median for all the runs, and sort of um, like the hurricane trail and the possibility of where it might go, uh, and the 20th and the 80th quantile of said days, and we end up with graphs like this. This become visualizations become more kind of visualization makes more sense when we have two scenarios to compare. Um, Again, these are counterfactual simulation without being calibrated for real world data. But um, utilizing this framework, we can see if we were to close schools in the given synthetic uh, simulated population of Campbellton, this is how the number of possible active cases reduce, and it's easy to communicate to public health and from public health to the rest of the population. Now, when comparing uh, more than two scenarios, it's simpler to just leave the median and the quantiles in the plot. For example, this is when we change the parameters of the contact tracing submodule, where we can compare with just with voluntary testing, and we can compare with in actual total infected and the reported cases. For example, the gap between reported and total infected cases with just voluntary testing is very, very high. And only with same day test tracing and testing, uh, we have, based on our simulation framework, we have the best case prediction of how it might capture the realities of the situation. So again, an example of the complexities this framework uh, makes it easy to simulate. There are other kind of visualizations that we can do. Since we are taking into account the venue of possible infections, we can compare uh, maybe just for this example, is just a single run, the count of new infections uh, for the particular venue type. Um, but obviously, so far, uh, the core of this framework relies on having an agent-based framework that captures the movement of a particular geography and a particular demography. But once their mobility simulation is done, it doesn't. Uh, we extract a contact network from it, and that contact network does not change based on the disease status or the disease simulation statuses of uh, uh, of an ongoing contagion simulation. So, which is far from reality, but it's a start. So far, we have simulated around 10,000 agents at max, Uh, we can do more, but again, those experiments are pending. We have not considered the mobility of a person within a venue, uh, which is again a simplification step that needs to be figured out. And obviously, the mobility model has been validated only for GTA. We are yet to validate it for smaller communities like the one we saw in the results, like Campbellton from New Brunswick. At this point, this framework gives uh, an approach to model heterogeneity fast and compartmentalizing disease model generation, validation, uh, the non-pharmaceutical intervention modeling and generation, and the human mobility, whether it's synthetic or generated from real-world data on three separate silos, which can be worked in parallel, um, and creates a space where we can uh, generate more counterfactual scenarios and faster, um, which may be uh, more important in the when the disease transmission has not reached a steady state. Um, so again, this is still a proof of principle, and the future work we hope to include multi-level contagion spread models where communities may feed to bigger communities up to provinces and nation states and so on. Would like to compare the modeling accuracy and efficacy with respect to synthetic and real-world contact network, and the entire conversation of parameter fitting this with real data is a separate project in itself, which is one of the cons for this model. Uh, and inclusion of non-individual entities like sea or water as a single source, as an output from this kind of framework, and so on. I may have rushed a bit and may have completed my presentations in nearly half the time allotted. So I would invite questions now, if that's okay.
Thank